Hello everybody, my name is Aaron Ezer and today we will be learning about the derivatives of polynomials. So looking back, you should already be familiar with the idea that instantaneous rate of change of a function is represented by the slope over the tangent at a specific point on its curve. You also learned that this slope can be determined by finding the derivative of the function using Newton's quotient, which is the first principle. This is the formula for it, and let's try it. So this is our function, and if we plug it in, we turn this part into the x plus h function, and this is just the normal f of x. Then you expand it, you collect like terms, then you factor out the h and plug in 0. That would give you the derivative. That was a lot of steps. Don't worry, mathematicians have derived a set of rules for calculating derivatives that make this process way more efficient. So this is the table of the derivative rules that they have discovered. So feel free to pause the video, and these are the examples of it. Let's try it. So this is the exact same question as we used on the limit one. So the first step to answer this is to just bring down the exponents, then subtract 1 to the exponents of the x's. So here we brought down the 2 in front of the x, and same with this one. But it's a 1 over here, but you just can't see it. But the 4, the constant rule says that any constant is 0, so it just turns into a 0. So f prime of x is now equal to 3 times 2 is equal to 6, x to the power of 2 minus 1, which is 1, plus 2 times 1 is equal to 2, x to the power of 1 minus 1, which is 0, and x to the power of 0 is just 1, so 2 multiplied by 1 is just 2. So this is the final answer. And let's identify some of the rules that we used. So we used power rule and constant multiple rule for both of these. But for this one, we use the constant rule. And for the end, we use the sum rule because these two terms, we derived each term, then we can just add it at the end to make it easier for us. Compare and look at the difference. As you can see, when we use the rules, it is way easier and way faster than using Newton's quotient. Now let's communicate our understanding by answering a couple of questions. How can you use slopes to prove that the derivative of a constant is 0? So this is a function y equals 1, and as you can see, that slope is y to minus 1 divided by x to minus x1. If x1 is 1 over here, y1 is, we can agree that's 1. But if x2 is at 4, y2 is also still 1, because it's just a straight line. So if we plug that into the formula, it's going to be 0 over 3, and the slope's going to be 0. So that just proves that the derivative of a constant is always 0. How can the sum and difference rules help differentiate polynomial functions? So f of x equals 3x squared. This is a normal question. We just derive this normally. But what if it's a longer question like this one? Then in this case, we'll have to derive each term separately, then just add it at the end. And that's how it helps us differentiate polynomial functions. Why can you extend the sum and difference rules to 3 or more functions that are added and subtracted? Describe an example to support your answer. Let's say f of x is equal to x cubed plus 4, g of x is equal to x squared plus 2, h of x is equal to 2x cubed plus x plus 7, and z of x is equal to f of x plus g of x minus h of x. Then z of x would be let's just plug in all those functions. It would be this big one right here. What if we want to find z prime of x? Then we'll have to derive each term separately. And if we derive f of x, is going to give us 3x squared. And if we derive g of x, is going to give us 2x. And if we derive h of x, is going to give us 6x squared plus 1. And that's how it would help us if we are answering a function that is just the subtraction and addition of multiple other functions. What is the difference between proving a derivative rule and showing that it works for certain functions? Proving a derivative rule, it shows the rule works for all functions that meet the conditions, uses mathematical reasoning and definitions like the definition of a derivative, and explains why the rule is always true. Meanwhile, showing a rule works for certain functions uses specific examples, only shows the rule works in particular cases, and does not guarantee the rule works for every function. Thank you for watching.